Hello guys, if you guys do remember me, it's me Nirjal. So last year in a video about the same computer RISC-Me, I told that I'm going to make a breadboard computer that I'm going to hang in my wall, play Pac-Man in it. This is me after like 6-7 months trying to make that computer, and this is going to be a video about me ranting about what I did in all these 6 months, like how I proceeded in making that project and all. And this is going to be a long, boring video about me talking about FPGA, like Verilog, like breadboard computer and all. So it might be boring for you all, so you guys can skip it. So basically, like I was introduced to the course called Computer Architecture and Design. It was a course of 3 credits in our university, and by that I really got inspired how to knowing what actually by actually knowing how computer works. And uh, like basically the concept was very new for me, and being a electric enthusiast, I really wanted to take that project as a semester project. And in a sixth semester, it's the last semester where we do semester project here in KU. So as a semester project this year, I did this project. So yeah, so there were many ups and downs, so I'm going to talk about those things too. And also maybe I'm going to go through the Verilog code that I have written, and I'm also going to show you guys the register level chart of how the computer works and all. So also I want to target this video to international audience too. So I'm thinking of sticking with English throughout the video, but I don't know, I might like move into Nepali once I like get panicked. But I don't know, let's start with the video. So basically, after starting with the computer architecture and design course, the videos of Bane Eater and all the YouTubers popped out in my YouTube, and like I was watching those videos 24/7 after that. And basically the concept of making a computer in a breadboard and making it work was awesome for me. So that was the main motivation for me. And also, like grab the knowledge I wanted to grab the knowledge about the basic computer architecture. Also, being an open source lover, I got to know that RISC-V was an open source architecture, so that also excited me to do this project. So that's all about the motivation and significance. So like I guess I have not introduced what the project is, but let's go. So this is a uh, semester project report. So I'm going to uh, like present what my project is on basis of this. So this might also be boring. I'm not into making presentations and all, but it's fine. So basically the project is named RISC-Me, and it's a 8-bit computer. And I got inspired by RISC-V architecture, and I initially started doing this project in breadboard, but due to the unavailability of materials and time, I was not able to do it in breadboard, so I implemented it in FPGA. So what I have done is I have like made a FPGA. I have written a code for FPGA to simulate this 8-bit computer, and I have also written a assembler for this computer too. So I'm going to get into that too. So let's start with the journey that I took. So basically in my YouTube channel, okay, where is my YouTube channel? So this is also going to be me uh, like navigating through my computer. I'm going to make this video on a single take because I don't have time to edit. So basically what happened is, on the course that I talked about architecture, computer architecture design and computer architecture design. So on that course, as a mini project, our instructor gave us to make one computer and simulate it somewhere. So for that, I and my team did like work on this computer. So it was a 32-bit computer. It was based in CISC, but RISC-ME was a cool name, so we like kept it that way. And after doing this project, I really got excited to implement it in a breadboard, and I thought like making a 32-bit computer on a breadboard would be a hassle, so I reduced the bits to 8-bit. Also, I read a lot about RISC-V architecture, and I tried implementing it in my computer this semester. So basically, it's a like 8-bit computer, and the instruction set for that computer is inspired from RISC architecture. And I have also made a similar for this computer. That's all. So let's go into the introduction part. So basically, like making a computer in a breadboard or FPGA and making your own computer with your own instruction is kind of a trend in a geek community, and it's a thing that's done by a lot of YouTubers. There are a lot of YouTube videos. There are a lot of like the subreddits in Reddit and all. So I also followed the same trend. And I called this computer inspired in RISC architecture, because in RISC architecture what happens is the instruction set is reduced into smaller instruction sets, so that the opcode is actually of lesser length than of normal complex instruction set architectures, and the executions of those instructions are also pretty much like lesser compared to the CISC architecture. So ideally in RISC architecture what's done is so each opcode is going to take one execution cycle. So I'm going to start by one example. So basically what happens is, if we want to like multiply two numbers, right, then what we do in CISC computer is that we create a opcode for multiplication, and even if it takes 2 to 3 execution cycle, we like put it into the instruction set architecture and we perform that activity, right? But in RISC architecture what happens is like we can perform multiply even by adding the same number multiple times, right? So in RISC architecture the clock speed is like made super high, and then the addition operation is performed multiple times so that the multiplication can be performed. So I guess you got the idea, right? So that's how the RISC architecture works. Also in a CISC based architecture, the execution cycle is extended because of like because of memory reference instruction. So basically so for any memory reference instructions, you need to like grab the value from memory using the address register and put it into one register and then compute it again. So it's going to take 2 to 3 execution cycle. But in RISC architecture there is instruction like store and load, by which like you do load and store operations primarily, so that it's only going to take one execution cycle for other instructions. That is, even if like basically in RISC architecture there won't be any memory reference addressing, and that's also like another feature of RISC. I'm like bumbling a lot, but it's just for my memory, so I don't know, like even if it's boring I don't care. So basically I guess you got the idea of RISC and CISC, right? So that's what so basically to make this computer based on RISC architecture, I tried incorporating those features. So basically I tried making every instruction of like a single cycle, and I tried making my computer's clock speed high. So that's what I tried doing, but eventually it's not what happened. I'm going to go into that later, but that's what I was trying to do. So talking about the objective of my computer, so The objectives was, one, I wanted to make a 8-bit computer. So basically, initially, as previously said, I wanted to make that computer in breadboard, hang it on my wall, and connect it with like VGA, and connect it with monitor and keyboard, and play a Pac-Man in it. But it was not possible, so I changed my project into making it in FPGA. So I wanted to make 8-bit RISC-V inspired computer in FPGA, and I wanted to do that. Second was, I wanted to make a assembler for that computer, and third was, I wanted to grasp as much knowledge as I can on RISC architecture. I guess my English is also not clear, and I'm not being able to portray what I have in my head, but I don't care. Only talking about the related works, these are the some related works that I got like multiple insights from. So starting with the first computer that I talked earlier, that's named Pac-Man. So it's a computer made by one YouTuber. It's a computer completely made using the RISC-32 instruction set. So basically, if you also want to get the instruction set of RISC architecture, you can go into the Google and search about the RISC-32 I, C, and so those architectures, and you're going to get the whole instruction sets too. So basically, it's going to be easier to create. So basically, you don't need to create an instruction set architecture in RISC, because it's open source architecture. So he also did that. And second is the Ben Eater, who is famous for making a breadboard computer. So I was also inspired from his 8-bit computer. And third is from the Kruglag. So he basically made a computer using the transistors, and he connected thousands of transistors, and made a computer to play Tetris game. And it was also awesome video for us, but it was a headache for him. So similar to those computers, these are also the examples of computers that people have made. And at last, there is one reference from a book named Manamoris. He's a pioneer for digital logic stops, and he also made the architecture for the simplest computer that's based on 8-bit. So basically, I wanted to make my computer better than the Manamoris computer, and I also wanted to implement the RISC architecture. But eventually, I was due to the time constraints, as well as due to the inexperience of me, the computer is more worse than the simplest computer that could ever exist. Even my computer does not even have the complete instruction sets and all. But I don't know, I'm just fumbling a lot, and I'm actually feeling a bit weird, but it happens. So basically, now let's move into the methodology. So talking about the methodology, so basically, I started with instruction set designing. So I designed the instruction sets, which I'm going to describe later. After that, I wrote the whole thing into the Verilog, and I made ALU, control unit, everything in Verilog, and implemented it. And third is, I flashed and uploaded into the FPGA, but currently it does not have any IO operations and anything, so I'm not being able to see it. So the outcome of my work is only the timing diagrams that I can show, and that's all. And fourth is assembler development. So basically, I wrote a assembler in Python. It's also not that matured assembler. Basically, there are no levels and loop in that assembler. It's basically assembler that's going to convert the operations and registers and into binary. That's all. It's also not complete, but it's at least showable. And after all those steps, the main problem was in debugging and simulation, and that was another methods that I carried in this video for debugging and simulation, I used iVerilog. So it's a program where you can simulate a Verilog code in your own computer, and you can see the outputs and all. And in iVerilog you can also write a test bench code. So basically test bench is like unit testing in general computing or programming. So basically in test bench you simulate like multiple scenarios that the component you wrote in Verilog can go through, and basically see its output and verify whether the output is matched or not. And from that test bench you can also create a VCD file, which is basically a timing diagram, and you can see those timing diagram into GTK wave. And basically that was what I used for debugging and simulations. Now let's move into architectural design of my computer. So basically my computer was based on von Neumann architecture, because the instruction and data was in a same memory, and memory was separated from a central processing unit. So for every instructions, the computer had to face from a memory and read it and execute it. So it's based on von Neumann architecture. So basically there are two types of architecture, von Neumann and Harvard. Harvard is mostly used in like digital signal processors and all, but I have not actually gone in depth about the Harvard architecture. Uh, but in architecture, basically the instructions and the data are separated in the memory, so that the different bosses are used for those, and that's how the Harvard architecture works up to my understanding. And after that I checked for the instruction set completeness of the program. So talking about the instruction set completeness, any computer needs to have at least arithmetic logical shift instructions, as well as the memory operations, and it also need to have the status checkers to be the complete computer. However, in my computer they are not shift operations, but we can do shift using the arithmetic and logical operations. So we can also count that. So basically my computer has instruction set completeness. That's all what I'm going to say. Now let's move into the instruction set architecture of our computer. So as previously explained, the old length is of 8 bits, and talking about the register, there is latch, increment, reset, data, and register out. So basically latch means write enable pin, increment means basically when you give high to increment and you run a clock once, then the value of register is like incremented by 1, and similarly the reset resets the register, and so on. So that's a basic register that the computer has. And talking about the another thing that computer has, it has sequence counter and sequence decoder. So basically as RISC have reduced instruction sets, we do not need that much of that high number of bits in register counter. So for that I made only 3 bits 3 bits sequence counter in my computer, and I decoded it into the 8 signals. So my computer goes from T0 to T7 for any control signals and all. And for memory I had only 8 bits available. I could have expanded it by like making it the higher number of bits, but for that I had to like combine 2 registers even to store that. So for that reason I made the memory of only 2048 bits. That means there would be 8 bits to indicate the address of the memory, so that there would be 2 power 8 different spaces in memory, and there will be 8 bits in each memory slot. So that's going to be equal to 2048 bits. I guess you guys are not understanding anything, but like let me proceed, I don't care. So basically that's what the memory is Only interesting thing is that previously when I like started making this computer, I was like fixed into one architecture, and in that architecture there were only 3 bits for memory, because of which I had to redo the whole thing again, and that was also one of the challenge. So if you guys are also making a computer, do pre-plan all the instruction set architecture before jumping into making a computer. Okay, so that's going to be easier, and you guys can basically go into that, yeah, immediately. Like, so basically you guys can directly conclude from one thing without like jumping into multiple things again and again. Also, okay, I'm already out of context, but basically I aim to make the computer in breadboard, so I started making it also. So here is a basic clock using 555 timer. So this clock was inspired by Ben Eater's video. So this LED works on all stable mode so that it blinks around easily, and here is a 555 timer on monostable mode. So basically when I guess it's bistable mode, so when I press the press this button, this LED goes on and off on each presses. And here I had a switch to control between these two. So for this I only use the D register present in 558 timer. So if you guys want to like go in detail about this clock diagram or this clock circuit, then you can go into Beniter's like video and have a look on detail there. So basically this is how it looks. I wanted to like make the whole computer this neat in breadboard, but I was unable to. But let's continue on where I left earlier. So basically talking about the instruction format. So there are two types of instruction format in my computer. So one is with 3 bits for opcode, 2 bits for operand 1, and 3 bits for operand 2. And this type of instructions are usually these types of instructions are for load store. These kinds of instructions are for and or and other instructions, but for load and store I have made another type of instruction format. So for this there is the 3-bit opcode, 3-bit operand 1, and address is stored in another word. So for load and store there is 2 word of instruction, and for other instructions there are only 1 word of instruction. So that's how my computer works. When you talk about the operations, there is add, subtract, and or. So add and subtract as arithmetic, and or as logical, and data transfer there is load and store. So yeah, so load and store, that's how it's going to work. And for load and store instruction it takes 16 bits, that means 2 words, as my one word is equals to 8 bit in this computer. And talking about the control flow operation, I have included the jump and break if equal instruction. I'm going to go into detail how this works like later. There is a chart explaining it, so I'm going to go based on it. And for IO operations, I'm using the memory mapped IO. So for any IO instruction you basically need to load or store the values in certain sector of the memory, and the IO needs to take the values from that and work like that. However, I have not integrated any IO things here, so I'm not being able to actually show it to you guys. Also, now let's move into the chart that I was talking. So talking about this chart, so basically there is three. So basically in add operation there is a destination and source. So basically how the operation happens is uh, so like you're going to add destination into source and store it in destination. So that means our destination means our destination plus our source in RTL. And in subtraction the same thing happens, and an or is also similar. For load, so basically you take the address from the memory and store it into the R destination register, and store in storing the value of R source register is transferred into the memory address. That's the address stored in the another 8 bit. And for jump and break if equal, so basically break if equal works if the zero flag is enabled, then it will jump into the address where address that's stored by our source, and jump also works similarly. On talking about the computer registers, there are 7 general purpose registers. And those general purpose registers are going to be our destination and our sources. And there is program counter, there is instruction register, and there is memory address register, and there is also a status register. In status register, only uh, 2 bits are actually used. Here I have included 3. I don't know if there is some mistake in this report, I guess. So basically there is 0 and carry flag. So basically only the 2 bits out of those 8 bits are used in status register. And talking about the addressing mode, there is register addressing mode. So basically on this table you can see that in add, subtract, and or there is register addressing mode used. And immediate addressing mode is used for load and store. So basically the immediate value of address is taken from the instruction, and the load and store works like such. And also there is register to immediate addressing mode. So register to immediate addressing mode works on jump and break if equal condition. And now talking about the bus organization, there are 3 buses. I know all these all these things are not actually like the best way. So this is just me experimenting with my thoughts. So it's not ideal. Also, as I previously explained, it's more worse than the simplest ever computer possible in 8-bit. So don't judge me based on this. So basically it's because of me being immature and me having less knowledge about computer architecture. So basically there are 3 buses. So basically there are 2 source buses and 1 destination buses. So every so data is data of every register is from the destination bus, and the and every values or every output of every registers and memory goes to all 3 buses. And from that, using the multiplexer of 3 is to so so using the multiplexer having 3 selector line, the input and output is choose. So I'm going to explain it on Verilog later. And talking about the timing and control, as I previously explained, that's how the basic control unit looks like. So basically from the 8 bits from instruction decoder and from the 8-bit of sequence counter, the control unit gives the control signal to each and everything of the computer. And talking about the timing, so the T0 and T1 is for fetch instruction, T2 is for decoding. However, I was not being able to find what happens in decode instruction. So decode time, so I have not explained it. While googling it also, there were no clear answers of what happens in decode operations. But I don't know, like there are not any register transfer happening in that instruction. So I don't think you need to invest another clock in it. But I might be wrong. But in Mona Morris book, there is also in Mona Morris book also uh, like the decode instruction is not clearly explained. So I might be wrong on this, but find it yourself about what happens in decode instruction. And if you guys come to any conclusion, do leave the comment down below. And talking about the execution cycle, so basically all the operations except load and store happens in T3 cycle. But for load and store, you add the you transfer the PC value into AMR, and then in timing 4 you face the instructions you face the value from the memory and transfer it into the register. So it's going to take another 1 more clock to do this operation. So that's what happens in load and store. So for load and store, it's not based on RISC, I guess. I don't know. I'm also learning and I might be wrong. So do fact check before like before coming into conclusion from this video. So this is the basic arithmetic state machine chart of my computer. So start happens, t0 and t1 is for fetch, t2 is for decode, and t3 and t4 is for execution. And talking about the software requirement, I have used Verilog, which is the hardware descriptive language. So basically, you can describe how you need your hardware and write it in Verilog, and it's going to make a hardware for it for you, and that's what the SDL and is. And Verilog is the program that was made in 1900s, and it came a long way. It had multiple revisions, and I worked on Verilog 2005 version for this program. And talking about SDL, there are multiple SDLs, like very high speed hardware descriptive language, that's called VSDL, and there is Verilog, and there is other hardware descriptive language too. And among those, Verilog is very similar to C, because of which it was easier to learn for me. Still, there were many confusions, uh, but basically Verilog is pretty easy to understand if you guys have programmed in C earlier. And talking about the Verilog, it's dynamically typed, so it's very prone to errors compared to VSDL and other hardware descriptive language. So in this project, I chose Verilog because it was easier for me to learn. But if you guys are concerned about the errors, and if you guys want to, like, I don't know, but Verilog and VSDL, it's heads to heads language, so using any of those will work. On the second program that I have explained earlier, Verilog, I use that. GTK Web also I use that. And they so basically the FPGA that I use for this project, this one, was Tang Nano 9K. It was like I landed this from Ashish. I thank you to you because you were the savior for this project. So if I had no FPGA, I'll have literally failed in this project, I guess. But basically, I did this project in this FPGA, and the chip used in this FPGA, this one, is made from a company named Goin, and they have their own EDA for programming and compiling the thing. But the programmer was not accessible through Linux, so I used OpenFPGA as Flash FPGA to flash codes into this FPGA. And for hardware, I used Tang Nano 9K, which I talked earlier about. Talking about the challenges, so basically availability of the material was the big challenge for me here in Nepal, uh, as the local stores did not have anything. If the materials were available on time, I'll have done the project in breadboard. However, it was not possible, as well as finding FPGA was also very hard for me. So I landed it with my senior. And so basically availability of the material is very hard was very hard, and it was actually a challenge for me. The second was documentation and familiarity with Gowin. So basically the errors that appeared in Gowin was completely new for me, and there were not enough documentation and community support for that too, because of which I struggled a lot. And the third was project management and planning. So basically in semester project, you do it in a team, but as I was as I took a project that was actually different from people's interest, I had no teammates, so I did this project alone. So which was also another challenge that I faced. And talking about the planning of the project, I could have figured out everything that I needed to do earlier, so that I could plan my time accordingly, but that did not happened. And so basically I started writing code in Verilog from day one, and I was not clear about instruction sets. And I came back from Verilog to instruction set, and went back and forth between those things, and I was doing multiple things at a single time. I also had to document all those things. So basically, project planning and timing was very challenging for me. And talking about the features, I have made a similar, and I've also made FPGA implementation of that code, and that's all about conclusion. So talking about the limitation, it not have any peripherals integration, so you cannot see what's actually happening inside the FPGA, and you cannot see inputs and outputs. So that's a limitation of this computer. And second is instruction set. As I previously explained, this computer is even worse than the Mona Maro's computer. Like that computer was made to teach people and like educate people about like designing computer and architecture. So it's made using very fundamental concepts, and it does very fundamentals works, but my computer does not even do those fundamental work. So it's also a limitations. And the third one is that there's no IO. So there's no IO, also there are no GPIOs integrated, so nothing happens actually. And talking about the future enhancement, I'm thinking of making a VGA BIOS and peripherals integration for this computer, so that I can play Tetris on it. And the second is expanding the instruction set. If I like get interest on making computer again, I'm going to scrape all this instruction set and start from very beginning. And that time I'm going to think about every aspect that can go wrong and work on that. And fourth is also want to make the thing real world deployable. But this is a report, this is a formality, so I've written anything that I want to kind of. So talking about the Gantt chart, this is only for showing purpose. That's not how the event planning and execution happened, but this is a Gantt chart, and this is the assembler that I'm going to show you later. This is a register transfer level view at FPGA. These are the timing diagrams of everything, and that's all. So let's see how much time that I have taken. Okay, it's already 37 minutes long, but let me go through Verilog code too, because I struggled a lot writing a Verilog for this computer. So let's start with this either. So okay, it's not this. Okay, I opened the wrong file. Okay, so I started writing the Verilog from the register. So this is the register that I made. So the register had clock, reset, latch and increment as input, also data as input, and register out as output. And so if there is reset on, then like put 0 into the register. And if there is latch enable, then latch means like write enable. If there is write enable, then basically write the register with the data that's coming from this input. And basically if there is increment, just add it by 1. So basically this is the register I made in Verilog. And for that register I have written a test bin. So in test bin, so basically I have created an instance of registers, and I have basically domed it into VCD. So it's a basic like boilerplate. And I have started with reset 1, and after 20 seconds of delayed I have set reset to 0, and I have added data and latch and checked if that's inserted there or not, and I have done increment here. And after that I have finished the simulations after 100 seconds. And every 5 nanoseconds, I guess, yeah, it's every 5 nanoseconds I'm going to invert the clock. So after that I could, so I'm trying to show you guys the timing diagram or the VCD that was generated from that thing. So basically here it is. So basically talking about the register VCD. So based on all those inputs that I showed you guys here, So from that the timing diagram is created like this. So basically let's input clock, data, increment, reset and latch. So you can see is things like this. So this is the basic output of my project. So basically this is a register. So when the increment is 1 in next clock cycle, the value is incremented by 1. So basically it was AA initially, and after this positive clock it converted into AB. So that's how I debugged, and that's how I checked each and every instructions in my computer. And after the register I created a array of general registers. So general register was registers from R0 to R7. These are the outputs, and for those outputs I have created 8 instances of the register that I have created here. And at every so here it should have been positive clock cycle, but asterisk means without even the positive value of clock it's going to switch. So at every time the register boss selector is selected, so the source 1 is outputted like this and source 2 is outputted like this. And talking about the latch enable, if the destination is selected then the latch is enabled and data is always going through these things. So every time the destination selector is selecting this register, it's going to get entered into this register. So that's how the general registers works. And talking about the ALU, so basically for ALU here these inputs: enable, input A, input B. So basically I have taken a mode directly, so that in this parameter.v file I have basically like defined all the possible constants that can happen in my program. So basically if there is add, subtract, and or in ALU, it's going to perform the similar operations. And for flag carry, this is how it happens, and subtract happens like such. And for 0 I have like done one ternary operations at the end, and this is how it happens. So I'm also new to Verilog, but if you guys are interested in learning Verilog, you guys can comment so that I can make a like video series. If you guys want, because of that reason I might also learn Verilog in detail, but I don't know, I might also not make it. But if you guys really want it, do leave a comment so that I can think about making it. So this was the hardest part of my computer, so I had to make a control based on all these signals. And basically in control I have like taken a sequence counter, and like on T3 I have I have run a switch case and operated based on this. So here I have just made ALU enable, and once the ALU enable is on, the ALU is going to do its operation. So basically I was also confused about how control unit work, but in short, you just like create or change control signals to control unit. So basically you don't write or read into any registers or sorts in control unit. So basically in control unit you just basically need to write on the selector thing, and the enable or any control signals are available. So basically you won't do any like operations in you won't do any operations like adding, subtracting, or anything like such in control unit. So you do each and everything in ALU, like every operations in done in ALU. And like control signal is handled by control unit. Every logical and arithmetic thing is handled in arithmetic and logical unit. So that's what you guys need to understand. And for basic transfer you don't need to control anything, it's just going to happen if you enable or disable the control signals. For example, here for loading I have just enabled, so I have just diverted the buses, and I have just made the PC increment on, and also the memory write on. So by doing all by doing only this, so basically I have just manipulated the control signal here. By only doing this, you are just going to like make things work. So that's how the control unit should work. Also in control unit, you are also going to handle this T1 like fetch and decode cycle. So you also need to understand that about control unit. When you talk about the boss, I have like made boss using this multiplexer. So basically I have like taken all these inputs, and this mocks output as output, and there is and based on this selector line inputted from here, the mocks output is going to be defined. So this is what the boss is. So basically, if you guys are having hard times on remembering what boss is, it's basically a multiplexer doing that thing, doing multiplexing. And that's all, I guess. Yeah, that's all. And this is a memory, this same as register. And in top I have made instance of everything. And so basically those were all the classes, or classes if you guys are familiar with OOP. And here I have made the objects for that, and I have handled everything from here. So nothing is instantiated between each other, and this is how things are done. And here are the test benches, and here are the VCD files. So if you guys want to check it out, you guys can check it out in my GitHub. So I'm going to leave the link in description below. And this was all that I did. And so basically I don't have any like VGA or any input output peripherals. I am not being able to show it physically, but it can be done if I create a peripherals. But it's just going to be the wrong investment of time if I do so in this computer, because it's like almost of no use. And that's all, I guess. That's all I wanted to say. And if you guys are also thinking of doing a project alone, semester project alone in KU, don't do it. So and second is, if you guys are thinking of making a breadboard computer, and then it's not possible as a semester project, because you guys will have hard times getting the material. So even if you want to do it in a semester project, do it like first gather all the things needed, then start writing a proposal for that. And it's going to take at least a year if you guys are only giving 2 to 3 hours a week. So that was how my time distribution was. Also, I don't know. So basically this was just a video for me as a memory. And if you guys have any queries or anything, you guys can just comment on. If you guys want to know more about Verilog, FPGA, or like anything, you guys can just comment so that community can help. And to check it out, you can visit my GitHub link. Also in GitHub I'll link my Notion, where I have like put everything while I was brainstorming. But the thing that I wrote in Notion initially was completely wrong because of improper planning done by me. But like if you want to check it out, also do it. So if you guys are also making a computer, like initially like just like make everything finalized, finalize instruction set, finalize everything, then only proceed on making a computer. At last I want to thank Dirasa for guiding me and helping me through the project. Also I want to thank Asisai, because of without whom this project will not have been possible. Also he was also one of the main motivation factor for doing this project. And third one, I want to thank Rajendra Dai, who helped me like get like components for doing so. So basically this breadboard and these components were also given to me by KU, but it was not but it was not enough, as well as I had very less time to do it in like breadboard, so I not did it. But yeah, so if you guys want to proceed with this, you guys can. I don't know, I'm just fumbling around. I do have lots of assignment to do too. So bye bye signer. I know I have like done multiple grammar mistakes. I have not talked well. I have like basically missed the basic structure of English and all. But and this is just me trying to make videos, and this is just me trying to like make memories for future needs also. That's all. Bye bye. Sayonara. Mata ne. Hello everyone, I forgot to show you guys the assembler that I made, so I'm quickly going to show it. Also my battery is draining down. So basically this is the assembler. So basically based on these opcodes and these registers, I have basically run the split operations and then a loop. So basically this assembler program is going to break based in line. This assembly line is going to convert this into the binary of single lines. And this is what I have done. I have not integrated any labels and loops here. I could have done that and it will have been better, but due to the time constraints I have not done that. So basically this is the assembly program, and after I run this script, the main.python file, which takes input file name and output file name as parameters, and after that it's going to convert this assembly file into this binary file. So what happens is load means 100, and R1 means 001, and the address of memory 1 is 1. So that's how things happen. So basically this is how the loads operations are going to happen. The comments are wrong here, and basically for add means 000, add means 000, and basically I'm okay. So basically that's how things are working. I guess this is the one, 000, 010 for R3 and 10 for R1, and that's how the add operation, and that's how similarly all the operations are going to happen on assembler. And that's all I wanted to say. That's what I missed. Sayonara, matane.